Well, welcome today to everybody. Our webinar that we've got going today, Teaching Survival and Reliability Analysis with JMP. We have one of our academic ambassadors, Ross Matusalem, who's going to be delivering the webinar. You should see a poll that popped up asking you about your familiarity with JMP and any other software that you might be using. We appreciate getting an answer to that. And at the end of the webinar, we're also going to pop up a poll that's asking you how we can help you further from the webinar. There's a chat where if you want to make general comments, or whether that's for us or for other attendees to see, you can make some comments like that in the chat window. But if you have a question, strongly encourage you, please use the Q&A panel in Zoom instead. It'll be much easier for us to track and answer the questions. I may periodically stop Ross if we have some questions that I want to have him address, but I'm going to be monitoring that as we go and hopefully being able to address all the questions as they pop up. And with that, Ross, are you ready to go?
Yes, I am. Thanks, Kevin. Can you hear me okay?
I can.
Beautiful. Everybody, thank you for taking a little time out of your day today to learn about teaching survival and reliability analysis with JMP. So both survival and reliability involve analyzing time to event data. And you might even title this webinar Teaching Analysis of Time to Event Data with JMP. But the methods most commonly used or the common terminology can differ sometimes between the survival domain and the reliability domain. Survival analysis may align more with biostat in medicine, where we might be concerned with survival time, perhaps in something like a medical trial. And reliability analysis, on the other hand, aligns more with engineering, where we're concerned with time to failure often for a product, a part, or a system. And other domains use time to event analysis techniques too. For example, business analytics might use them to model customer churn or turnover. But of course, in all these different domains, underlying them are just the techniques for analyzing time to event data. And so that's what our focus is today. And JMP has a large suite of tools in the survival and reliability area here. And so you're going to find them if you go to the Analyze menu and look at reliability and survival. And you see a pretty large list of JMP analysis platforms here. First thing to note, if you're ever wondering what some of these do, go ahead and hover your mouse right over them and you'll get a nice tooltip. So here I can see that the Life Distribution platform fits and compares distributions of time to event data. JMP, as I said, has a large suite of tools. As you can see in the notes in my JMP journal on the left, you have your standard or core non and semi-parametric methods. So your Kaplan-Meier estimates and survival curves, your proportional hazards models. On the parametric end, you have your core methods of just estimating your time to event distributions and also building parametric survival models. And then a suite of more specialized or advanced analyses that may be relevant to some, but probably not all of you, though some certainly would be taught in certain courses. Today, the goal is to get you acquainted with the tools for the core foundational analyses that are going to be covered in most courses. So that's those non-parametric and parametric methods that I've listed there. We'll have a few minutes at the end to see a couple of the more specialized tools just for those who are interested. And as usual, in our webinars, our teaching-focused webinars, we're assuming that you already have a decent background in the statistical methods that we're talking about here, and that you're really here to review the JMP tools and teaching resources that you need to use JMP effectively in your course and with your students. And so that's the focus today. So let's get started first with the non and semi-parametric methods. And for the examples that we're going to see here, we're going to stick in the biostat and medical domain before moving on to the engineering domain in the parametric methods. So we're going to begin with Kaplan-Meier or product limit analysis. That is just characterizing survival curves and estimating survival probabilities with non-parametric methods. And we're going to use the RATS sample data set. This comes bundled in JMP. I should mention at the end, you might see in my journal there, we're going to talk about teaching resources, and I'm going to show you where to access every sample data set that you see today, as well as some additional teaching resources. So in this data set, which references a study by Pike published in 1966, but as described in the popular Kalbfleisch and Prentice book from 1980, we have a study of carcinogenesis, so cancer, in rats. And for a simple analysis up front, what we're going to do is take the survival time in the study of each of the 40 total rats that we have in our data table and conduct a basic Kaplan-Meier analysis. And before we do, I'll just note, if you look over at our censoring column here, I can click right in that header graph where it says 1, and that is a censoring code, indicating that we have, in this case, if we look down here, we can see we've selected 4 rows. We have 4 out of 40 right censored observations. So for example, in row 11 there with a value of 204, that was the final observation we had of that rat, day 204. And as of that date, the rat was still alive. And I should mention, and I had it in our notes actually at the top here, that in addition to all of these methods that I've listed or JMP tools, they accommodate censoring whether you have right, left, or interval censored data. And I'm going to show many examples of right censored data, but I'll also show you how to set up analyses for left and interval censoring as well in just a little bit. But back to our rats example here, we're going to conduct a basic Kaplan-Meier analysis, and I'm going to introduce you to the tool for it, and I think maybe some things to know about using it for teaching. You can see a simple Kaplan-Meier curve plotted here. We also have statistical summaries. So for example, I can see again that we have 4 censored observations, that the mean survival time in this study was 230.7 days. I also have the quantiles, so the median survival time and the upper and lower quartiles, and a full table of these Kaplan-Meier or product limit estimates here, along with some additional information. For example, the number failed at each time point, or that is the number of rats that died, and the number at risk. So let's see how I actually set this analysis up now that we know where we're going and some of the things that we find in the data here. So Kaplan-Meier analysis is inside a tool or a platform called the Survival Platform, and you're going to find it under Analyze, Reliability and Survival, and Survival down near the bottom here. So let's launch that platform. I know we have a few folks here who are not JMP users. This might be the first time you're seeing a JMP launch dialog. In each of these, we take the list of variables or columns from our data on the left and just put them into the certain analysis roles on the right. So we'll take our days column and put it in the Y or time to event role. I'm also going to take this censoring column, if you remember, that's just 1s and 0s over here, and put it into the censoring role here, and JMP will handle the censoring for us. One thing to note when you are declaring censoring in any of these tools, you will also have some option to declare what value in your censoring column actually indicates censoring. In this case, it's listed 1 by default, and that aligns with what we have here, but we could easily change it if we want. So when I click OK, I get the basic report out. And this contains all of the information that we actually already saw. So we have that Kaplan-Meier curve, the statistical summaries, and then the full table of estimates, number at risk, and so forth. Now, one thing to note, if you're teaching your basic non-parametric survival probably pretty early on in a course, you may also teach the confidence intervals around these survival probability estimates. Those were in our plot originally, but they aren't shown by default. So if you want to turn those on, head on up to the red triangle and look under the plot options, and you'll find the ability to turn on confidence intervals as well as several additional options for you here. So in our example at the beginning, I had the simultaneous confidence intervals turned on, shaded specifically. You also can find pointwise intervals here as well. So I've set that up. If you want to set that as a default, which I imagine many folks for their teaching might, just know that under the red triangle and platform preferences, you can always save these preferences to your global JMP preferences so that those are turned on every time. So again, just to review what we have here, we have the summary stats that are found in the summary and quantiles table. A couple more things to note. The summary table, that's going to tell us just generally about our data. So again, the mean survival time, the number failed or died, and then the number censored, you're also going to notice here that it says biased, and in much statistical software, if you see something like that, you may be alarmed at first. That's indicating to us here that the final observation we have is censored. And so if we go down to row 40, you're going to see that this rat was observed at day 344 and actually was censored, so was still alive on that day. So that's all that means there. The quantiles, as we saw, you have your median. You actually have a lower and upper 95% confidence interval on that median, and then the lower and upper quartiles as well. And then this combined table down below, again, is the full Kaplan-Meier estimates. And one thing I want to point out here, because I've had a number of JMP users bring this up in the past, they look at this and sometimes want to work with this table further. In fact, I've encountered a number of people that want to be able to add the at-risk values to the Kaplan-Meier plot, for example. And as you'll notice, that's not included, and it's actually not an option up here. So this is just a nice trick to know about JMP in general. If you ever have a results table and you want to work with it in other JMP tools, you can always right-click and go to Make into Data Table. And now I have that as a JMP table. And I could, if I wanted, maybe build a more customized Kaplan-Meier curve plot in, say, Graph Builder or something like that. So I just thought I would point that out because I've had at least a few people in the past ask me how they can actually get that table out and work with it. Now, looking at the name of the table, combined, you might be a little confused by that. The idea here is that this platform, the survival platform, can also handle group comparisons if you specify a group variable at launch. And so the combined table just means combined across any groups that were provided. We didn't provide any groups here, but if you go back to our data table, I'm going to right-click here where it says group, select hide, unhide, to reveal a column that specifies two different groups in the study. So you might think of, one is a treatment versus control group in a basic medical study here. So let's actually add that grouping variable and see what we get out. So we're going to go back to that survival platform. Here's another quick tip for you JMP users. If you click the recall button in any of these launch dialogues, it'll populate it with the same setup the last time it was launched. So that was a little shortcut for us. Now I can take that group variable, put it into the grouping role, and click OK. And now I get the same output as before, but you can see everything's broken out by group 1 versus group 2. So looking at the survival plot, it looks like survival in group 1 is a little more favorable than in group 2. We can see that in both the means of the two groups, so 241 by 219 approximately. Same thing for the medians, but if we look now, whenever we specify a group variable, we get our chi-square tests, and all the way on the right there, we see our p-values. For the two tests, 0.08 approximately and 0.1. So if we were being strict with a 0.05 threshold, we would say we don't have statistical evidence of a difference here. And you'll notice we also now get the full estimates tables broken out by group 1 and group 2, and then also combined here. So this combined table is the same as the one that we saw before. So this survival platform is the first place to go, I think, when teaching just non-parametric survival, which, if you look at tables of contents in many textbooks or syllabi, is often the first thing taught in a survival or reliability course. And this is, I think, a nice, simple tool to get going with students here. Under the red triangle, you will see that there are more options than what we've shown, the basic non-parametric analysis here. For example, you can fit a few different distributions. For example, if you wanted to fit a Weibull distribution to the data, you could also do competing cause analysis. But the outputs are generally limited to those that are probably going to align reasonably well with the content early on in a survival or reliability course. Now, thinking about group comparisons here gets us towards our next topic, and that is thinking about how explanatory variables affect survival curves here. And so we're going to move on to proportional hazards models, so a semi-parametric way of assessing the effect of explanatory variables on survival rates, where we don't actually assume an underlying distribution. So let me actually close down the rats data set and pull up another example data set that you can find bundled in JMP. And again, at the end, I'll show you where to access all of these data sets. This is another one from Kalbfleisch and Prentice here, the VA lung cancer data, where we have data on 137 lung cancer patients in a clinical trial. They had one of 4 different types of lung cancer. We also have some additional information about each patient. For example, if they're undergoing a standard or test or experimental treatment. We also have their KPS score, which is a measure of how debilitating the disease is, where higher values indicate less debilitating. And then, of course, we have their survival time and whether or not any of these observations were censored. So if we look, for example, in row 18, we have an individual that's right censored at 83 days. So it looks like at 83 days, they dropped out of the trial. And at that point, they were still alive. So we're going to build a proportional hazards model here using the proportional hazards platform. So you can see we have 2 statistically significant effects here out of all of our explanatory variables, KPS being the most, followed by cell type. Down below, we have our parameter estimates and also the baseline survival estimate plotted right here with the full table of values down below. More information on our statistical tests, again, likelihood ratio and Wald. And then finally, our hazard ratios. So a common thing for us to look at in a proportional hazard model here. So for example, if we wanted to look at that effect of KPS score in more detail, we can see that the hazard ratio per unit change in KPS is 0.97 approximately. So that means for each increase in 1 point of your KPS score, your hazard rate decreases by a factor of about 0.97. And that might not actually sound like that much, but when you keep in mind that if we go back to our data, if you just look right here in this header graph, values range from 10 to 99, 1 point is actually not that big of a difference. And if we look at, let's say, the overall range hazard ratios for KPS going from 10 to 99, then we see a very small value. So going from a very low to a very high KPS score dramatically reduces your hazard rate. So this is a proportional hazards model in JMP. Let's actually see how I fit it here. We're going to go to Analyze, Reliability and Survival, and Proportional Hazards. You'll find it living all the way down at the bottom of the Reliability and Survival submenu here. Here is the launch dialog where we specify the form of the model. Now, I know we have a lot of JMP users, probably some pretty experienced out there, and you may be looking at this and saying, that sure looks like the dialog from Fit Model. And for many of us who may be familiar with the Fit Model platform, which is just a general purpose linear modeling platform. And this is when we launch the proportional hazards option under the Analyze menu, what it does is it takes us into Fit Model and then uses the proportional hazard personality. So it's really just a shortcut to a particular point in a more general tool. And so if you're a more familiar JMP user and prefer to just go straight into Fit Model and choose proportional hazard, by all means, have at it. So anyways, let's set our model up. We're going to put our time to event at the top here. You can see we also, again, have our censoring role. So I'm going to take that censoring variable and put it there. You'll notice in this tool and some of the others we're going to look at, you'll again have a place to specify your censoring code and a little red triangle next to it, which will allow you to select among the different values in that column. And so in this case, we've selected censored automatically because that's first alphabetically. So we'll just leave it there. And then finally, down below, I can build out our model effects. So if I select all of our explanatory variables and click Add, I'll get a basic main effects model. I could also use the cross button to create interactions or quadratic terms or other thing or whatever terms you would want in your model. You can also use the macros down below if you want to, for example, create a factorial to a degree of 2 or a full factorial model. Now, whatever it is you want to do. For our purposes here, we're just sticking with a main effects model. So I'll click Run. And as you can see, the output is containing essentially everything that we just saw. So this default output is going to include almost everything for the proportional hazards model. So we have, again, this effect summary, which I left implicit before. This is, if you haven't seen this in JMP before, it's a rank ordered list of all your model effects by statistical significance, so smallest p-value at the top. So again, we can see that we have just two statistically significant main effects here of KPS and cell type. Under the whole model section, we have some fit statistics and a statistical test on the whole model fit. So it looks like we are explaining some variability in our response here. Again, we have the parameter estimates table. So each estimated standard error and the lower and upper 95% confidence limits. Again, baseline survival estimate. And then you can see at the bottom, we have more information on the statistical tests here. And if you'll notice, actually, just go ahead and map the p-values that you're seeing in the effect summary. For example, 0.0003 for cell type, and you'll find that that corresponds to the likelihood ratio test here and not the Wald test. So you're seeing the likelihood ratio test being reported up there in the effect summary if you're curious and if that's important for your course. So the only thing we're not seeing in the default output is those hazard ratios, but certainly we want to display those for interpreting our model. And so I will choose hazard ratios from the red triangle to bring those back up. And you can see for our continuous regressors, we get both unit and range hazard ratios, depending on which one we want to look at. And then for our categorical variables, so for example, here's cell type, we get the hazard ratio for every possible combination. So for example, right here, we see large over adeno with a hazard ratio of 0.45, indicating that relative to the adeno cell type, patients with the largest cell type have a hazard rate reduced by a factor of 0.45 on average. And so this is the proportional hazards output. As you can see, I only invoked one red triangle option here to get those hazard ratios open. And other than that, that's basically what we get from this platform. It's a pretty standard statistical output, I think, for this kind of model. But one thing, if you're familiar with JMP, and even if not, I'm about to show you something that you should get familiar with and that we're going to see more throughout the rest of the webinar. And that is that when we build models, it can be helpful to have a visual representation of the relationship between the factors of the model inputs and the response or outputs. And so here's an example of the same proportional hazards model, but with, in this case, what we call a quantile profiler, which allows us to, for example, change some input values, like we'll set cell type to large. We'll say that somebody is in the test treatment. Maybe they were 65 years old, and we want to know what the median survival time is for that individual according to this model. And here we can see that is 153 weeks. And this is one of several profilers that we might use. So here's one where instead of inputting the quantile or probability and getting a survival time out, we can put in the survival time along with our explanatory variables and get a survival probability out. Or here we have another one that is actually giving us the hazard rate right here. So these profilers can be quite useful. And if you are teaching with JMP Pro, then you're going to find these in FitModel's generalized regression personality. So let me show you how to set that up, because I think if you're teaching proportional hazard models and you have access to Pro, this could really be a helpful way to make the models a little more accessible or concrete for your students. So I'm going to go to Analyze FitModel. And as you remember, I mentioned that you could always go to FitModel and then just choose proportional hazards under the personality menu, which is what we've been doing so far. But I'm actually now going to go up to generalized regression. And under the distribution here, I can choose Cox proportional hazards. And then we'll set it up the same way as before. Time goes into the Y. I'm going to add main effects for our explanatory variables, put our censor variable in, make sure that we've selected the correct value here, and click Run. Now the model output, we have, again, our Cox proportional hazards model. We have our parameter estimates. We have our effect tests here. We can invoke, say, our hazard ratios if we want, but here's where we can find the profilers. And so I'm going to bring up that quantile profiler again, which we were using to find survival times at the median according to various explanatory factors here. And so if you have Jump Pro, again, this is how you can set up the analysis in generalized regression instead of the dedicated proportional hazards platform to get access to these profilers. But as we saw before, the standard proportional hazards model under that reliability and survival submenu that you're going to find down at the bottom here will still build that model for you and just give you everything but those profilers.
Ross,
Yes.
question for you is there a way to sort of check some model assumptions? Pop down that red triangle. I can't remember if there's.
Let's see. So we do have some diagnostic plots. This is just going to plot the baseline survival and hazard. So one thing to keep in mind here in a proportional hazards model is that we're not making any underlying assumptions about the distribution of these survival times in this case. It's one of the benefits there. So we don't, as we would in a traditional regression model, maybe need to check some assumptions about the appropriateness of the distributional assumptions that we're making. Here, that's not so much of an issue. Any other questions that might make sense to handle right now, Kevin, before we move on to the parametric methods?
One just popped up, and I'm just reading it now.
Okay. Well, for the sake of time, I'll keep moving along, and if it makes sense, we can loop back around to it. All right. So those are I think, really the two core tools and techniques. So the survival platform, the proportional hazards platform, for teaching these non and semi-parametric methods that are often taught by my understanding or knowledge somewhat early in a typical survival analysis course. Now we're going to move on to parametric methods. So these are methods that actually involve assuming a particular distribution that has generated the survival times that we're looking at. And actually, I shouldn't say survival times. We're going to move on now from the biostat and medicine domain that we've been in so far to engineering here. And so the first data set we're going to look at, this is a data set that was recently added to our library of teaching materials at jump.com, thanks to our friend Kevin, who's hanging out in the Q&A right now. This is on the durability of bone plates. So let me actually pull up a PDF here to illustrate. So we're talking about a medical device, a plate that you would actually fasten to a fractured bone to facilitate the healing process. It's basically a structural support. And we're testing the durability of these bone plates using a flexure testing machine, like the one that you're seeing here. So we place the plate in the machine, and we repeatedly apply downward force on it, and see how many cycles of force are applied until the plate deforms. And when it deforms, we would count that as a failure. And so here I have the number of cycles to failure for 64 tested bone plates right here. And I have another censoring column here, where in this case, we have a nominal variable where we've written no fail for censored and fail for those that were not censored. And we're going to now begin by estimating what I'll call here a life distribution, a common term in the reliability domain for these data. And so this is what that looks like. So now I'm in Jump's life distribution platform. I've actually fit a log logistic distribution to these data, and you can actually see that plotted on the right there. I've done that because I was actually able to fit and compare numerous distributions to these data and identify the log logistic as the best fit. And down below, I have the information on that distribution. So here are estimates of the location and scale parameters, along with their confidence intervals. And I have a set of profilers. So in the distribution profiler, for example, I can change the number of cycles on the x-axis and see what the cumulative failure probability would be predicted by the distribution that we fit. So for example, if I want to know at 4,200 cycles, what proportion of bone plates would have deformed, my best point estimate there is 0.16995. So let's see how I would do this analysis. I'm going to close down our report here, and we are going to go to the life distribution platform in the reliability and survival submenu. So let's pull up life distribution here. I'm going to take cycles to fail and call that my Y, or time to event. I'm going to put fail as my censoring column. And again, I have my red triangle right here. I'm going to choose no fail. Make sure always to get your censoring value in the censor code specified correctly before getting going. And with that, I will click OK. So you can see, unlike some of the tools we've been seeing so far, much of the statistical outputs that you might generate using this tool actually aren't shown by default. And in part, that's because we have yet to ask it to fit any distributions to these data. But before we do, I do want to note that you can perform Kaplan-Meier analysis. In fact, that is provided by default. You can see when we're looking at this plot of our data where we have cycles to fail on the X and the cumulative failure probability on the Y here, we have a Kaplan-Meier curve, just a non-parametric curve here. And if I go down to the non-parametric estimate, you will actually find your Kaplan-Meier estimates here. So these are the same estimates that you would get in that survival platform that we started out with. So if that's the case, why did I show you the survival platform? And it's because, to me, the survival platform is nice and simple. And if we're beginning a course or early in a course, maybe introducing students to Kaplan-Meier, it might make sense in many cases to use the simpler tool. As you'll see, the life distribution tool is capable of a lot more. Now then, let me close this back up and actually highlight to you something that you might miss because it's minimized by default. But it's this event plot. And what it does is visualizes each row's failure time. I want to make this a little wider. And I'm going to go ahead and stretch the axes out a little bit here so that we can see what's going on. And I'm going to do this with our data table to the side. So for the event plot, we have 1 point for each row in our data table. So 64 in all. Those depicted with an X, like this one, which you can see back in my data table now, is just the first row, are those in which we've observed a failure. And in this case, a right-facing arrow indicates a right-censored observation. And then you can see we just have the dotted line carrying forward, indicating that we are not sure when in that time period failure actually would have occurred. This plot is a nice, I think, once you learn how to interpret it a little bit, clear way to quickly visualize your data and maybe learn some new things about it. So for example, I can see all of those right-facing arrows are at exactly 5,000 cycles. So now I know, if I didn't before, that it seems like at 5,000 cycles is when we stopped the reliability test on each plate here. I can also see, for example, that we have nothing but solid red lines going up to and just past this 3,000 cycles here. So I already know right off the bat that there were no bone plates that failed before that point. So the event plot is a nice, helpful way to visualize your data. Don't miss it. It is minimized by default. So let's bring up this compare distributions section now, where we had that non-parametric plot right here. Note first that we are plotting a life distribution, or in this case, cumulative failure is what we're really looking at here over number of cycles. And if you're teaching survival using this platform, you may want to actually plot a survival curve instead. And you can by going to the red triangle and just choosing show survival curve. So it's up to you. We actually have that off by default here. In an engineering domain, it's probably more common to look at things this way. Now, finally, we can use this compare distribution section to fit and compare multiple distributions. For example, let's fit the good old Weibull distribution here. So I can see the distribution fit. I can even change the scale to a Weibull scale if I want. And down below, I have these statistics. So I have right here some basic fit statistics. So if you're familiar with the AIC or BIC, they're measures of goodness of fit, where lower values indicate a better fit. And I have the full statistical details for that Weibull distribution. So I have, for example, my parameter estimates right here and all the profilers down below. So I can fit and compare multiple distributions. Let's do a log normal distribution as well. That's now overlaid on the plot. It's been added to our table. We can see that by AIC and BIC, it's about as good of a fit as a Weibull distribution is. Now, instead of clicking on these one by one, you can go to the red triangle and select one of these options: fit all distributions, fit all non-negative, fit all defective subpopulation distributions, to fit and test many distributions against each other at once. So if I, for example, select fit all non-negative, we see that according to the AIC and the BIC here, lowest values go to the log logistic. And so I might choose to work with that distribution further. But of course, if I've done that, and really maybe for the purposes of our course, we've been talking a lot about, say, the Weibull distribution, I can always still pull that output up. And so you get these profilers to explore the distribution a little more. We already saw the distribution profiler. We can put, in this case, cycles to fail in and get cumulative failure probability out. We can, in the quantile profiler, do the opposite. So maybe I'll say, at what number of cycles would I expect cumulative failure, or 0.1, or so where would I see my 90% reliability cutoff? And that's just shy of 4,000 cycles. We also have a hazard profiler here, if we're interested in the hazard rates. And then finally, in the density profiler, we actually can see a visual depiction of the distribution, in this case, the Weibull distribution that we fit. So these profilers, which are provided automatically in this case for each distribution you try, are a great way to interactively explore the distribution that you fit to your data. And I should mention that we're only scratching the surface here of the life distribution tool. You could go a really long way, I think, in teaching many topics in a reliability course inside this tool. So if we go to the top red triangle, you're going to notice we haven't even talked about, for example, fitting mixture models or competing risks. If we go down to a particular distribution we fit, we can do things like fix one distribution parameter and then re-estimate the other. We can even do Bayesian estimation if we like. So this is a pretty full-featured tool here. I just want to point that out without getting too deep into the weeds here. For folks who are interested, as I imagine some might be in more details in this tool, you'll receive a follow-up email from us to send the link to the recording and these materials to you, and you can always just reply to that and ask for some help or some more information. Now, before moving on to the parametric survival models, so as we did with the non-parametric methods, we look first at just estimating, the survival, or in this case, failure, distribution or curve, and then look at the effective explanatory variables. That's what we're going to do here. But I do want to take a moment, and I'll use the event plot as an example again here, to talk about handling censoring. We've been looking at right-censored data the entire time. And so again, in this event plot, we have a bunch of right-facing arrows that are showing that we have a good number of observations where at 5,000 cycles, the bone plates didn't fail. What if we have a situation where we actually have left-censored or interval-censored data? How would we handle that? And I'm just going to use this as a simple example because we're here for no other reason. Let me pull up a different representation of these data, and I've made a couple modifications here. So you can see I actually have two columns now representing time to event. I'm going to pull up a life distribution using these two. I should mention that in order to do that, all I would do is just go to life distribution, select both columns as my time to event, and click OK. And so what do we see here? Let me just move this over. So again, I have X's for points where we actually observed failure. And you can see back in my data table, the first row selected, it shows in both columns 4,516. And so that is indicating here that we have an observed failure at that time point. What about a right-censored observation? How is that represented? Well, we have in the cycle 1 column, if you look to the data table, a value of 5,000, and then no value, a missing value in cycle 2. And that's representing to the life distribution platform that this is a right-censored value. Now, what about a left-censored value? We can actually see one right here, a left-facing arrow. So all we know is that failure occurred at some time before 3,173 cycles here. And if we look in the data table, you can see we've set that up as a missing value for cycle 1 and a known value for cycle 2. Now, finally, what about an interval censored value? We actually have one right here. And if you look over, that's in row 15. You can see that we have two arrows facing each other. And if you look at the data table, cycle 1 equals 3,980 and cycle 2 equals 4,200. So we have two values that are different, capturing the interval in which failure happened. So this is how you can handle left and interval censored data in JMP. You use this 2-column format where if there was no censoring, you have the same value. Again, that's like row 1. For right censored data, you have a value in the first column only. Left censored data, you have a value in the second column only. And then interval censored data, you have 2 different values in the 2 columns with the earlier value in the first one. And so then if you notice, let me pull up how we filled out the launch dialog again. I don't have to declare a censoring variable here. If I put these 2 in, JMP knows that I'm using a different format to do that. So you can use that censoring variable when you just have exclusively right censored data. Otherwise, you're looking for this format here. So that's just a bit of an aside, but I know that's a common question we receive. And so I want to make sure you understand how to set that up appropriately. All right. So now let's talk parametric survival. And we'll pull up yet another example here. So parametric survival, we're just looking at, again, the effect of explanatory variables on our distribution of survival, or in this case, failure times, but we're assuming an underlying statistical distribution for those failure times. Close up our bone plate example. And here's another data set that comes bundled in JMP, the computation time data set. This is from the classic textbook from Meeker and Escobar, Statistical Methods for Reliability Data. Actually, the second edition of that book, I think, has been out for a couple of years now, adding Francis Pasquale as an author. This is taken, from the original, where we have as our time to event the time to the completion of execution of a computational task under varying degrees of processor load here. And I like this example. It's a simple way of looking at the effect of one continuous variable on a time to event variable. And also that time to event variable, you'll notice, is not failure time. It's not survival time in a medical study. It's just the time it took to complete a computational task. And this is a nice way of highlighting to students, perhaps, that again, we're just talking about time to event. An event might intuitively be something like a failure, but it doesn't have to be. And certainly if you're teaching in business statistics, it would be, say, time to somebody canceling their account or something like that. So let's take a quick look at what output we're going to build here. We're going to fit this parametric survival model where we have underlying log normal distribution assumed. Here we have our parameter estimates, hypothesis tests, a quantile plot. So in this case, we're looking at lines representing the lower and upper deciles and also the median of the assumed log normal distribution as load increases. And then we have quantile and distribution profilers. So with this quantile profiler now, for example, I could say, what is the median time to completion under a load of 2.5? And I can see that's 185 seconds right here. So let's set this analysis up using the parametric survival platform. I'm going to go to Analyze, Reliability and Survival, Parametric Survival. I'm going to put execution time as my time to event, load as my effect. You'll notice here, once again, we are in a fit model using a specific personality, the parametric survival personality. You'll notice that we can also select which distribution we want to use. I'm going to actually select all distributions here, and then it'll fit and compare multiple distributions for me. You'll also notice that we can specify location effects and then also scale effects as well. For simplicity's sake, I'm going to leave it at just a location effect of load right now. And also we don't have any censoring here, so I can just leave all of this blank and click Run. So because I had all distributions selected, we tried these 5 distributions listed here. And by both the AIC and BIC, we actually have identified the Frechet distribution as being the best. But if you look at some of these values, you'll see that both the log normal and log logistic aren't too far behind. And so you might have some flexibility depending on which distributions we're actually teaching in our course. It would seem that in this example, at least the one we might not want to use, and I'll click on it in our distribution overlay plot, here is the exponential distribution, which sure is lying pretty far away from all of the others. And we can also see that according to our fit statistics is doing quite a bit worse. So we have a separate parametric survival model that's actually been built for all of these different distributions. We saw that the Frichet was technically the best, but maybe we want to go with that log normal distribution. And when we look at the output for that, again, we get all these default outputs. So this is much like the case with the proportional hazards output, where we get almost all the information really that we could want, at least initially by default. So that's, again, our parameter estimates, our tests, our quantile plot. I did mention and show that you can get distribution and quantile profilers, which you're going to find under the red triangle. So they live right down here. Now here we also can take a look at our residuals if we want. We are assuming an underlying distribution right now. We can also estimate survival probabilities or quantiles in batches. For the sake of time, I'm not going to show exactly how this works. They're all pretty straightforward. You just go to the red triangle and evoke the option that you want. One thing I do want to point out, though, is that in this platform, here I should have left that up, we have access to the distribution and quantile profilers. But much like with the Cox proportional hazard models, we can get a little bit more if we used generalized regression if we have JMP Pro. So if I fit the same model in generalized regression, you'll notice I get a prediction profiler, which is actually showing us the mean predicted execution time under varying loads. We have that distribution and quantile profiler, but I also actually get a survival profiler. So I can see survival here means that the job is still going. So maybe at a load of 5 and 400 seconds, how many jobs will still be running? It looks like just shy of half of them. And we have a hazard profiler here as well. So if you want to use those additional profilers, you can set this up pretty easily. So let's go to fit model here. I'm going to click recall to get back to where we were before, but instead of the parametric survival model or personality, excuse me, I'm going to choose generalized regression. And then under distribution, I can choose the distribution that I want to use. So we were looking at a log normal before. So I'll continue with log normal and click run. And now we have the same model fit in a more general purpose JMP tool with the ability to pull up those profilers. So for example, the survival profiler right here. And you'll notice, the parameter estimates and everything match what you will get out of the parametric survival platform. One downside to doing things this way is that if you want to model the scale parameter as a function of one or more explanatory variables, that's not supported here. You'll have to use the parametric survival model platform for that. But in case you want to use some of these additional profilers and you have JMP Pro for you and your students, I wanted to point out that those options are there. All right, so we just have a couple more things I would like to show you before we wrap up and then answer what remaining questions we have. I think we've shown you some tools that hopefully will get you a long way in your course. So that is whether you're using parametric or non-parametric methods, or maybe you're teaching both, for just assessing the survival time or failure time distributions, and also for exploring the effect of explanatory variables. And actually, one thing that I didn't show for the sake of time, I should at least mention, I think it was in the notes, that FitLife platform that we saw, much like the survival platform, can take a grouping variable as well and perform some basic by group comparisons along those lines. Now let's take a quick look at a couple specialized methods. If you remember at the beginning, I mentioned things like competing risk and recurrence, degradation models, accelerated life testing, these things that are probably only going to pop up maybe in some of your courses. But I want to give you an idea about how some of these things work, at least with 2 examples. And I'm going to do these really high level just to give you an idea of some of the additional possibilities here. And first, we're going to take a look at the default data set. This is another one borrowed from Meeker and Escobar's textbook. And this is from accelerated life testing. So if you're not familiar, in accelerated life testing, we take an acceleration factor, let's say temperature, and we use it to induce failures in something in a shorter amount of time. Because if we tested things under their standard operating conditions, they would take forever to fail. So if something would take 100,000 hours of operation to fail at normal operating conditions, we can't really reliably gather a lot of data in a reasonable amount of time. But if we crank up the temperature, maybe they'll fail much faster. Then we can build a model that relates temperature to the failure distribution, and then use that to go back down to normal operating conditions and see what the failure distribution is likely to look like. And so this is what we have here. We have a number of products with their failure times in hours. We also have whether they were censored, and we have their operating temperature here. So 10 degrees is standard operating temperature, but we've also tested 40 degrees and 60 degrees and 80 degrees, and this is all Celsius. And there's a specific tool in JMP that's great for the analysis of accelerated life testing data. Actually, I should mention right now, you can also design accelerated life tests using JMP's DOE tools. You'll find the option right there. But let's go to our Fit Life by X platform, which, as the tooltip says, models life distributions parameterized by just a single regression factor. But as we're going to see, it actually has some nice tools specific for analyzing accelerated life testing data. So I'm going to say that hours are my time to event. My X variable here is that temperature, that acceleration factor. I also have my censoring variable. And I skipped over briefly this weight column, and you can see actually the value is 1 for many of them, but 30 in this case at 5,000 hours and 90 here at 5,000 hours and so forth. And so what the weight is showing is how many units we tested, and in this case, were censored at a particular time point. And so you can think about it as saying, take this row and replicate it 30 times, because we had 30 tested units that had the same values here. And so that's another format that you might be able to use here, especially if you have a long data table with rows that contain the same information. You can just have it once with a weight and put that in a frequency role. Now, it's nice here under the relationship dropdown, you have a number of different relationships, and these are underlying formulas or equations that relate the acceleration factor, so in this case temperature, to the underlying distribution that we're going to use to model the data. And so for Celsius, actually, the Arrhenius-Celsius equation is a particularly good one to use. I'll click OK. You'll notice that we've modeled it with a log normal distribution, but I have the option to change distributions here. I get a Wilcoxon test here, which is just testing for differences among the various temperatures. If you'll notice, actually, if we check out the summary of data and the plot, we have a high number of right censored values, 132, and actually down here at an operating temperature of 10, we don't see any points. We actually didn't have any failures there at the standard operating temperature. Nevertheless, thanks to our model, which is using that Arrhenius-Celsius equation right here. So here's the equation and the parameter estimates. We have our profilers. So we can say, for example, at an operating temperature of 10 degrees Celsius, what is the cumulative failure at 5,000 hours? And we can see that it is vanishingly small. What is that? I always struggle to translate scientific notation accurately on the fly, that 0.006%. Or we might go to the quantile profiler and say, again, at our standard operating temperature of 10 degrees, what's the 90% reliability time? We get 60,500 hours of operation approximately. So this is just a quick bit on the Fit Life by X, specifically for accelerated life testing, though it can handle any situation where you just have one regressor. We could have actually done our computation time analysis in this platform as well. And you'll see, though, again, that it has some things built into it to make accelerated life testing analysis a little easier. So the acceleration equations, and also we have the ability to control some aspects of the report based on the acceleration use condition, which again here was 10 degrees Celsius. Let's see. We'll do this last one, degradation analysis, in just 1 minute or so here. In degradation analysis, instead of having a single point in time at which something dies or fails, we have a characteristic of something that slowly degrades over time. For example, we have the gallium arsenide laser data set, another one bundled in JMP, where we have a laser, and as the electrical components of those lasers degrade, the necessary operating current increases. So a value of 0 here represents the standard operating current, and up to 12.2 is that current increasing. And we might say that actually a laser needs to be replaced once the increase in necessary operating current hits a value of, let's say, 12. So in JMP's degradation platform, what we can do, just to kind of give you a quick example, is perform a statistical analysis. Actually, no, I'm going to do it from scratch because then it'll be easier to put in that 12 cutoff here. So pardon me while I do that. I'll go to the degradation platform. I'm going to say that current is our response, hours is our time, and unit, we have multiple observations over time per unit or laser here is our label or system ID. And then that upper spec, when we normally would replace one of these lasers, is 12 amps over standard operating current. And so what's happened here is we've fit regression models, just linear models that actually take for any given unit or laser here, the data and extrapolates out to when in number of operating hours that laser would have hit that current increase of 12 and need to be retired. We can see that actually only one laser that we observed, 110, actually did in the time period of our study. And so what we can do then is ask for those crossing times, those times that we predict each laser would have hit 12 amps. Now we have those predictions out and can put them into the life distribution platform and, for example, fit a Weibull distribution to them. So we didn't actually observe the, quote, failures of these, but we were able to project when those were likely to occur and then actually fit a distribution to those values and then use that distribution to make some additional inferences. So that's kind of a very brief overview of degradation analysis and one use of it in JMP. There are actually multiple uses of degradation analysis. A big place is in stability testing in the pharmaceutical industry to be used to set expiration dates. And the degradation tool in JMP, if that's something that you're teaching, actually has built-in stability options as well. But for the sake of time, we'll leave JMP tools behind. And now I'll just take a couple minutes to show you where to find all the teaching resources, like the data sets we saw today, before finishing up with the remaining questions that you might have. So first off, to find many of these data sets, you can go to the sample index under the help menu. So if you go to sample index and look in the reliability and survival section here, you're going to find, for example, here's the default data set that we just looked at for accelerated life testing. We also have the rats data set, the VA lung cancer data set, and a number of others as well. And actually, there are even more than are listed here. This is kind of the list of the, best data sets you might want to consider, but you can always click this button that says see the alphabetical list of all sample data sets, and you'll find some others as well. For example, that gallium arsenide laser data set is actually living right here, and a lot of these are helpfully labeled, so reliability in this case. And you'll notice some other reliability data sets here as well. Aside from that, I recommend just going to jmp.com/teach to find maybe some other data sets and additional teaching materials. So I'm going to do that right now. When you land at jmp.com/teach, you're going to see a listing of course topics, and reliability and survival is near the bottom under advanced courses. And if you click there, you're going to see a number of different sections where we suggest various JMP teaching resources. Just a couple to point you to. Under these step-by-step guides, which are brief tutorial videos and one-page PDFs on how to use JMP tools, if you click View Recommended, you're going to find a couple entries specific to some of the tools we saw today. So here's the one for using the life distribution platform to fit distributions to time to event data. And you'll see this is just about a 2.5-minute video walking you through the basics of using the life distribution platform with an accompanying guide you can download and take with you. These are nice videos and guides to post maybe to your LMS, link to on your syllabus. So when students are looking for that quick tutorial, oh, how do I use the life distribution tool to do some of that homework I was doing, you can avoid some of those emails, and they can take those questions straight to the video. And then finally, I want to point out the enhanced data sets. These are relatively new. Our friend Kevin has put together a number of sample data sets on a variety of different topics. So this is where the bone plate durability test data set came from. And if you click download on any one of these, you're going to get a zip file that's going to contain the data set and an accompanying PDF. And we actually already saw the PDF for the bone plate data right here. And all of these contain some suggested tools that you can use with this data set, a problem statement describing the data in more detail to kind of bring the data to life, And then some suggested exercises as well down at the bottom. And so these enhanced data sets, when we say enhanced, we mean enhanced with these accompanying materials, are particularly good for maybe structuring or providing an example in a lecture, forming the basis of an in-class activity, or maybe even assigning for homework. And so in the domain of reliability specifically, we have this bone plate durability test example posted here.